October 17, 1943. 11:43 p.m. The Markham River, New Guinea. Beneath the black surface of the mountain river, American combat divers worked in absolute silence. Chief Petty Officer James Mitchell of the 2nd Naval Construction Battalion pressed his breathing apparatus against his lips, exhaling a controlled stream of bubbles that dissolved into the darkness above. 40 feet below, his hands guided a massive steel caisson into position against the riverbed. The cylindrical foundation chamber, weighing over 3 tons, settled into the excavated pit with barely a vibration. Above the water, Japanese observation posts scanned the opposite bank through field glasses, seeing nothing. No lights, no sounds, no indication that enemy engineers were constructing permanent bridge foundations directly beneath their positions. The darkness provided perfect concealment for an operation that would have seemed impossible to any military force in history. Mitchell's diving partner, machinist's mate Robert Santos, connected the pressurized air lines that would allow construction crews to work inside the submerged caisson. Their compressed air equipment, borrowed from civilian bridge construction and adapted for combat operations, functioned flawlessly in conditions that Japanese military doctrine had never anticipated. At 2:17 a.m., the first railroad bridge pier emerged from the Markham River. By dawn, American locomotives would be crossing water that Japanese forces had calculated would provide a minimum 3-week defensive barrier. The enemy commanders sleeping in their bunkers 2 miles downstream had no idea that their strategic plans were already obsolete. The Pacific War had become a deadly chess match of islands and waterways where every river crossing and mountain pass represented weeks of potential delay for advancing forces. Japanese military strategy depended entirely on, and these natural barriers to provide predictable defensive advantages. Their war college had spent decades calculating exactly how long American forces would need to overcome destroyed bridges, crater-filled airfields, and strategic river crossings. These calculations formed the backbone of Japan's entire defensive strategy across thousands of miles of Pacific territory. General Hideki Tojo's staff had based their island-hopping defense on simple mathematics. A destroyed 200-foot bridge should require minimum 3 weeks to rebuild using conventional military engineering methods. Mountain rivers with swift currents and rocky bottoms demanded even longer reconstruction periods. Japanese engineers had proven these timelines during their own construction projects in China and Manchuria, where similar obstacles had consumed months of intensive labor using traditional methods. The Japanese understanding of military engineering reflected their own capabilities and limitations. Their forces operated with equipment that had changed little since the Russo-Japanese War 40 years earlier. Manual pile drivers required 20-man crews and could install perhaps 6 foundation pilings per day under optimal conditions. Hand tools limited daily earth moving to quantities measured in cubic yards rather than the hundreds of yards that mechanized equipment could manage. Most critically, Japanese military doctrine assumed that all enemy forces operated under similar constraints. This fundamental miscalculation would prove catastrophic. While Japanese intelligence services meticulously tracked American unit movements, ship positions, and troop strengths, they paid virtually no attention to engineering capabilities or construction methods. The Imperial General Staff focused exclusively on traditional military assets, battleships, aircraft, infantry divisions, and artillery batteries. Construction equipment, if considered at all, was dismissed as logistical support rather than combat capability. American forces approaching the Pacific in late 1942 represented a completely different philosophy of warfare. The United States had mobilized not just its military, but its entire industrial capacity for combat operations. This mobilization included revolutionary approaches to military engineering that Japanese planners had never encountered. Where traditional armies brought soldiers to fight battles, Americans brought entire industries to fight wars. The Naval Construction Battalions, activated in March 1942, embodied this industrial approach to warfare. These units recruited directly from civilian construction trades, bringing commercial expertise that no military force had ever possessed. Master carpenters became combat engineers. Heavy equipment operators traded bulldozers for tanks, then traded back again when construction demanded their civilian skills. Welders, electricians, and concrete specialists found themselves building airfields under enemy fire with the same efficiency they had demonstrated on peacetime projects. Each construction battalion deployed with equipment that amazed even American regular forces. 18 bulldozers per battalion provided earth-moving capability that exceeded entire Japanese engineering regiments. Power shovels, concrete mixers, pile drivers, and specialized construction machinery accompanied every unit, creating mobile industrial capability that could function anywhere American forces could establish a foothold. But the real revolution was organizational. Traditional military engineering followed rigid sequential procedures: survey the site, design the structure, gather materials, begin construction, complete the project. American construction battalions operated like civilian contractors under wartime pressure. Multiple crews worked simultaneously on different phases of the same project. Materials arrived based on predetermined specifications rather than detailed surveys. Construction began before design was finalized, with modifications made during the building process itself. This approach horrified traditional military engineers, but produced results that defied conventional calculations. Projects that should have required months were completed in weeks. Obstacles that should have stopped advances for extended periods became minor delays measured in days rather than seasons. Most importantly, construction proceeded at rates that made defensive planning based on engineering delays completely worthless. The technological gap between American and Japanese engineering capabilities represented more than equipment differences. It reflected entirely different approaches to solving construction problems under combat conditions. Japanese forces relied on proven methods that emphasized careful planning, precise execution, and acceptance of time requirements that natural obstacles demanded. American forces treated every construction challenge as an industrial problem requiring immediate solutions regardless of conventional limitations. This philosophical difference became apparent in the first major Pacific operations. When American forces captured Guadalcanal in August 1942, they inherited Henderson Field, a partially completed airstrip that Japanese forces had abandoned. Traditional military doctrine would have required extensive surveys, detailed engineering studies, and systematic reconstruction following established procedures. Instead, the 6th Naval Construction Battalion treated the damaged airfield as they would any civilian construction emergency. Working around the clock in 12-hour shifts, they applied civilian contractor methods to military construction. Multiple crews attacked different problems simultaneously. While one team filled bomb craters, another laid pierced steel planking for runway surfaces. Electrical crews installed lighting systems while heavy equipment operators expanded aircraft parking areas. The result was operational airfield capability in timeframes that violated every Japanese calculation about American engineering capacity. The Bailey Bridge system, adopted from British designs but manufactured in American quantities, provided the most dramatic example of this new approach to military construction. Each Bailey panel measured exactly 10 feet by 5 feet and weighed 570 pounds. But these standardized components could be assembled into bridges spanning any distance up to 200 feet without requiring heavy cranes or specialized equipment. More importantly, the entire bridge could be assembled on one bank, then pushed across the gap like extending a massive drawer. Japanese observers watching Bailey Bridge construction reported these operations to intelligence services that simply couldn't process what they were seeing. Enemy engineers appeared to be constructing complete bridges overnight where impassable rivers had existed the previous day. Traditional bridge construction required weeks of foundation work, pier installation, and careful span positioning. Bailey bridges eliminated all of these time-consuming steps through prefabricated components that could be assembled by trained crews in hours rather than weeks. The underwater construction techniques that accompanied Bailey Bridge installation represented even more radical departures from conventional military engineering. American forces deployed combat divers equipped with compressed air apparatus originally designed for civilian bridge construction projects. These divers could install bridge foundations in flowing water, rocky riverbeds, and conditions that traditional methods couldn't address at all. Caisson construction, borrowed directly from major American bridge projects like the Brooklyn Bridge, allowed American engineers to create permanent underwater foundations without requiring the water level to be lowered or diverted. Massive steel cylinders were sunk to the riverbed, then pressurized with compressed air to create dry working spaces below the waterline. Construction crews could work inside these underwater chambers, excavating foundation sites and installing permanent supports while river water flowed normally overhead. This technology had never been adapted for military use before World War II. Japanese intelligence services had no framework for understanding or countering construction methods they had never encountered. Their military engineers trained in conventional techniques that assumed all construction required dry working conditions and extensive preparation time. Seeing permanent bridges appear overnight challenged every assumption their doctrine contained about American capabilities. The scale of American construction operations amplified these technological advantages beyond Japanese comprehension. By 1943, over 325,000 Naval Construction Battalion personnel were deployed across the Pacific, representing construction capacity that exceeded the entire Japanese engineering corps. These forces operated with equipment inventories that included thousands of bulldozers, power shovels, trucks, and specialized machines that Japanese forces had never seen in military operations. Most critically, American construction operated with material abundance that eliminated the resource constraints Japanese engineers accepted as normal. Bailey Bridge components arrived at forward bases in quantities that allowed multiple simultaneous construction projects. Concrete, steel, fuel, and specialized materials flowed through supply networks that maintained stockpiles despite intensive consumption rates. Japanese forces, operating with limited resources and extended supply lines, simply couldn't match construction rates that assumed unlimited material availability. The human dimension of this engineering revolution centered on men who had never expected to build bridges under enemy fire. Corporal Frank Morrison had spent 15 years installing commercial foundations in Chicago before joining the Naval Construction Battalions. His expertise with pneumatic caissons and underwater construction techniques made him invaluable for Pacific operations, but nothing in civilian experience had prepared him for building railroad bridges while Japanese snipers fired from the opposite bank. Morrison's diving operations in the Salamaua campaign required him to work 40 feet underwater, installing foundation pilings for a 180-foot Bailey Bridge while enemy artillery targeted the construction site above. The psychological pressure of performing precise construction work in complete darkness, knowing that any mistake could compromise the bridge and delay the entire advance, pushed civilian skills to limits no commercial project had ever demanded. Yet Morrison and thousands like him adapted civilian expertise to combat conditions with remarkable success. The technological angle revealed innovations that transformed military engineering permanently. Bailey Bridge construction employed launching techniques that seemed almost magical to observers unfamiliar with the underlying principles. The complete bridge was assembled on the departure bank using standardized panels and connecting hardware. Specialized launching equipment then pushed the entire structure across the gap, with the bridge cantilevering over empty space until it reached the opposite bank. No heavy lifting equipment was required at the destination, eliminating the need to establish construction sites on both sides of water obstacles. This launching method allowed bridge construction to proceed even when enemy forces controlled the opposite bank. American engineers could assemble complete Bailey bridges while protected by their own positions, then launch the finished structure across contested water in operations that took hours rather than days. Japanese defenders watching these launches reported complete bewilderment at construction techniques their own engineers couldn't duplicate or counter effectively. From the intelligence perspective, Japanese miscalculations about American engineering capabilities represented systematic failures that undermined their entire Pacific strategy. The Imperial General Staff had based defensive planning on engineering delays that American forces consistently eliminated through superior technology and methods. Intelligence reports from field commanders describing overnight bridge construction were initially dismissed as exaggerations or misidentified. Enemy activities. Colonel Takeshi Mori of the Japanese 41st Infantry Regiment filed reports from New Guinea describing American bridges that appeared to be constructed overnight across rivers his staff had identified as impassable barriers. His superiors at divisional headquarters assumed these reports described temporary pontoon bridges or ferry operations rather than permanent railroad spans capable of supporting heavy locomotives. The systematic underestimation of American engineering capacity reflected intelligence failures that extended from field observation to strategic planning at the highest levels. The tactical angle demonstrated how construction speed became a weapon that destroyed Japanese defensive calculations. Traditional military doctrine assumed that natural obstacles would provide predictable delays, allowing defending forces time to prepare secondary positions, bring up reinforcements, and organize counterattacks. When American forces eliminated these delays through rapid bridge construction, Japanese units found themselves facing continued attacks without the breathing space their defensive strategy required. The Salamaua operation provided the clearest example of construction speed determining tactical outcomes. Japanese forces had positioned defensive lines based on calculations that the Komatum River would halt American advances for minimum 2 weeks. When the 114th Engineer Combat Battalion completed a 120-foot double-story Bailey Bridge in 14 hours, Japanese positions became untenable overnight. Sherman tanks appeared on ground that Japanese commanders had calculated would remain tank-proof for weeks, forcing immediate withdrawal from carefully prepared defensive positions. Enemy perspective revealed growing demoralization among Japanese forces, who watched their strategic advantages disappear faster than they could adapt their tactics. A diary records, veered from Lieutenant Hiroshi Tanaka of the Japanese 20th Division, recorded his unit's psychological impact. June 18, 1943, the Americans cross rivers like they are roads. Yesterday the Markham was our protection. Today their tanks attack from ground we thought impossible to reach. How do we fight enemies who build faster than we can destroy? This demoralization reflected more than tactical surprise. Japanese military culture emphasized spiritual strength overcoming material disadvantage, but no amount of courage could compete with construction capabilities that eliminated natural barriers as defensive assets. Units launching desperate attacks against American construction sites suffered devastating casualties while barely affecting construction operations that continued despite direct combat. The moral dimension involved American engineers who transformed military necessity into personal pride in craftsmanship that enemy forces couldn't match or understand. These men built bridges not just to achieve military objectives, but to demonstrate American industrial superiority that Japanese forces couldn't counter through traditional military means. The industrial angle revealed the overwhelming material advantage that enabled American engineering superiority throughout the Pacific Theater. A single Caterpillar D7 bulldozer generated 80 horsepower through steel tracks that could grip any surface, moving 200 cubic yards of material per hour. This exceeded the daily output of 100 Japanese laborers using hand tools. But the comparison understated the true disparity because American forces deployed thousands of these machines, while Japanese engineers operated with equipment unchanged since the previous century. Manufacturing capacity determined construction speed more than individual equipment performance. Bailey Bridge components arrived at Pacific bases in quantities that supported simultaneous construction projects across hundreds of miles of advance. American factories produced these standardized panels faster than Pacific forces could consume them, creating material abundance that eliminated resource constraints Japanese engineers accepted as normal operational limitations. The supply network supporting this construction capability represented logistical achievement that Japanese planners had never anticipated. Transport ships delivered complete construction equipment packages to captured islands, including bulldozers, power shovels, concrete mixers, generators, and specialized tools required for immediate construction operations. Japanese forces, operating with extended supply lines and limited shipping capacity, couldn't match material flow rates that maintained forward stockpiles despite intensive construction consumption. The strategic angle demonstrated how construction speed compressed the timeline of Pacific conquest beyond Japanese defensive calculations. Islands that enemy forces expected to hold for months fell to American attacks supported by infrastructure that appeared faster than defensive preparations could be completed. Each successful island capture became a construction base for the next advance, creating operational tempo that Japanese forces couldn't match through conventional military responses. Tinian provided the ultimate demonstration of American construction scale overwhelming Japanese defensive strategy. Between July 1944 and May 1945, 15,000 Naval Construction Battalion personnel transformed a captured Japanese island into the world's largest bomber base. Northfield contained 4 parallel runways, each 80,500 feet long and capable of launches. Hing B-29 superfortresses for 3,000-mile missions to Japan. Japanese forces had spent months fortifying Tinian using traditional methods, but American forces rebuilt the entire island as an industrial facility in timeframes that made enemy fortifications irrelevant. The psychological warfare angle revealed how American construction capabilities demoralized Japanese forces more effectively than direct combat operations. Enemy units could fight American soldiers with reasonable expectations of tactical success, but they couldn't compete with engineering capabilities that eliminated every natural advantage their defensive strategy required. Watching bridges appear overnight across rivers they had considered impassable barriers created despair that no amount of military training could overcome. Japanese commanders reported increasing difficulty maintaining unit morale when their carefully planned defensive positions became worthless overnight due to American engineering operations they couldn't prevent or counter. The captured diary of Major Kenji Nakamura from the Philippines campaign recorded this psychological impact. February 15, 1945. We destroy the Agno River Bridge, certain this will delay enemy advance for weeks. Their tanks cross on new bridge within 36 hours. How do we fight forces that rebuild faster than we can destroy? The technological evolution angle showed how Pacific operations accelerated engineering innovations that changed military construction permanently. Underwater foundation techniques developed for combat operations influenced post-war commercial bridge construction. Bailey Bridge principles became NATO standard for tactical bridging and remain in use today. Heavy equipment modifications for Pacific conditions, advanced bulldozer and excavator design beyond peacetime development rates. Combat requirements drove innovations that peacetime construction would have taken decades to develop. Portable concrete plants, automated mixing equipment, and specialized foundation machinery appeared in Pacific operations years before civilian industry adopted similar technologies. The integration of civilian construction expertise with military requirements created technological advancement that neither sector could have achieved independently. The cultural angle contrasted American industrial problem-solving approaches with Japanese military traditionalism that couldn't adapt to construction warfare. American engineers treated every obstacle as an industrial challenge requiring immediate solutions regardless of conventional limitations. Japanese forces approached construction problems through established military procedures that emphasized careful planning over rapid execution, making them unable to match American construction speeds or counter American engineering innovations. This cultural difference extended beyond construction techniques to fundamental military philosophy. Americans viewed engineering capability as combat power equivalent to artillery or aviation support. Japanese forces considered construction as a logistical activity separate from combat operations, preventing them from understanding or responding to American engineering warfare that eliminated traditional barriers between construction and combat phases of military operations. The night of October 23, 1943, marked the moment when Japanese defensive strategy collapsed entirely. Across 4 separate river crossings in the Huon Peninsula, American engineers simultaneously launched the most audacious construction operations in military history. Working in complete darkness to avoid enemy observation, they deployed underwater construction techniques that Japanese forces had never encountered and couldn't understand. At the Markham River crossing, Chief Petty Officer James Mitchell led a diving team that installed permanent bridge foundations 40 feet below the surface, while Japanese artillery periodically shelled the construction site above. The psychological pressure was extraordinary. Mitchell and his divers worked in absolute silence, communicating only through predetermined hand signals, knowing that any sound could alert enemy observers to the construction operation proceeding beneath their positions. The technical challenge seemed impossible even by American engineering standards. Compressed air caissons weighing over 3 tons each had to be positioned precisely on the rocky riverbed, then pressurized to create dry working spaces where construction crews could excavate foundations and install permanent supports. Any mistake in positioning or air pressure management could collapse the entire operation, delaying the advance and potentially costing hundreds of lives in subsequent fighting. Mitchell's team completed the underwater foundation work in 6 hours and 17 minutes, working entirely by touch in water so murky that visibility extended less than 2 feet. Above them, American engineers assembled a 180-foot double-story Bailey Bridge using launching techniques that eliminated the need for construction equipment on the enemy-controlled opposite bank. The complete bridge was assembled on the American side, then pushed across the gap like extending a massive drawer. Japanese observation posts 2 miles downstream reported no unusual activity during the night. Their lookouts saw no lights, heard no construction sounds, and detected no indication that permanent railroad bridge construction was proceeding directly beneath their defensive positions. The complete stealth of American construction operations reflected technical mastery that Japanese military training had never anticipated or prepared to counter. At 05:47 hours on October 24th, the first American locomotive crossed the Markham River on tracks that Japanese intelligence had calculated wouldn't exist for minimum 3 weeks. The psychological impact on enemy forces was immediate and devastating. Staff Sergeant Robert Martinez of the 533rd Engineer Regiment described Japanese reaction. Enemy observers on the hills just stood there staring at our bridge. You could see them with binoculars, not moving, like they couldn't believe what they were seeing. The Ramu River crossing, proceeding simultaneously 60 miles to the west, demonstrated even more advanced underwater construction techniques. Combat divers from the 2nd Engineer Amphibian Brigade installed pneumatic caisson foundations in flowing water while working entirely below the surface to avoid enemy detection. These foundations supported a 240-foot railroad bridge that appeared overnight where Japanese forces had positioned defensive lines based on the assumption that American advances would halt for weeks at this natural barrier. The speed of multiple simultaneous bridge construction operations overwhelmed Japanese defensive planning entirely. Intelligence reports reaching divisional headquarters described American bridges appearing at 4 different river crossings within the same 12-hour period. Staff officers initially dismissed these reports as impossible exaggerations, but reconnaissance flights confirmed that permanent railroad bridges now spanned water obstacles that had formed the backbone of Japanese defensive strategy. Colonel Takeshi Mori, commanding Japanese forces in the central Huon Peninsula, filed an emergency report to his superiors that captured the military implications. Enemy construction capabilities exceed all previous estimates. Natural barriers calculated to provide weeks of defensive advantage eliminated overnight. Defensive positions based on engineering delays no longer viable. Request immediate strategic guidance. No strategic guidance came because Japanese military doctrine contained no provisions for dealing with construction capabilities that eliminated natural obstacles as defensive assets. The Imperial General Staff had based their entire Pacific strategy on engineering delays that American forces consistently overcame through technologies Japanese intelligence had never studied or understood. The Sepik River operation, the 4th simultaneous construction project, revealed the ultimate extent of American engineering capabilities. Working in water 18 feet deep with swift currents, American divers installed bridge foundations using caisson techniques that required workers to function in pressurized underwater chambers for extended periods. The physical demands were extreme, but the technical achievement was unprecedented in military engineering history. The psychological impact extended beyond immediate tactical consequences to fundamental questions about Japanese military capability. If American forces could eliminate major river crossings overnight using construction techniques that Japanese engineers couldn't duplicate or counter, what other assumptions about enemy capabilities were wrong? How could traditional military planning function when basic calculations about natural obstacles proved completely worthless? Lieutenant Hiroshi Tanaka's diary entry from October 25th recorded the demoralization spreading through Japanese ranks. Our commanders planned defensive lines based on rivers that no longer stop the enemy. They cross water like roads. They build permanent bridges faster than we can plan attacks against temporary positions. We fight enemies who control the landscape itself. This realization marked the turning point where Japanese defensive strategy acknowledged its own obsolescence. Natural barriers that had determined military planning for centuries became minor inconveniences that American engineering eliminated faster than enemy forces could adapt their tactics to new realities. The dawn revelation of October 24, 1943, shattered Japanese military confidence permanently. As morning reconnaissance flights surveyed the Huon Peninsula, aerial observers reported what seemed impossible: 4 major railroad bridges spanning rivers that had been impassable barriers 24 hours earlier. The bridges weren't temporary pontoon structures or hasty field expedients. They were permanent steel and concrete spans capable of supporting heavy locomotives and military traffic that would sustain American advances indefinitely. General Adachi Hatazo, commanding the Japanese 18th Army, received these reconnaissance reports with disbelief that quickly transformed into strategic despair. His defensive planning had depended entirely on natural obstacles, providing predictable delays that would allow time for reinforcement, repositioning, and counterattack preparation. When American forces eliminated these delays through construction capabilities his intelligence services had never detected or analyzed, the entire defensive framework collapsed. The technical achievement represented more than rapid construction. American engineers had accomplished underwater foundation work in conditions that Japanese military doctrine considered impossible for any construction operation. Installing permanent bridge supports in flowing water, rocky riverbeds, and enemy-controlled territory required capabilities that no military force in history had ever possessed or attempted to develop. The simultaneous nature of these operations amplified their psychological impact beyond the sum of individual achievements. Japanese commanders realized they weren't facing isolated engineering successes, but systematic American capabilities that could eliminate natural barriers across hundreds of miles of defensive terrain. If rivers that had anchored their strategy for months could be spanned overnight, no geographical advantage remained secure against American construction capabilities. Lieutenant Colonel Samuel Sturgis Jr., commanding the 36th Engineer Combat Regiment, documented Japanese reaction in his official report. Enemy observation posts monitored our bridge sites for days without understanding what they were seeing. They couldn't comprehend how complete bridges appeared overnight where impassable rivers had existed the previous day. Their intelligence system had no framework for processing construction capabilities they had never encountered. The strategic implications rippled through Japanese command structure as field reports confirmed that American forces were systematically eliminating every natural obstacle that defensive planning required. The Markham River crossing compromised 3 separate defensive lines that had been positioned based on engineering delays that no longer applied. Japanese units found themselves retreating from carefully prepared positions because the natural barriers protecting their flanks had disappeared overnight. Major General Korochika Anami, commanding Japanese forces defending critical supply routes, summarized the impossible situation in his final message to Imperial headquarters. Enemy rebuilds what we destroy faster than we can destroy what they build. Defensive calculations based on engineering delays are no longer valid. Request revised strategic guidance for operations against forces that control construction timing. The underwater construction aspect created particular bewilderment among Japanese engineering officers who understood bridge construction requirements from their own experience. Installing permanent foundations below water level required specialized equipment, trained divers, and construction techniques that Japanese military engineering had never attempted. The idea that American forces could perform such operations in darkness, under enemy fire, and in timeframes measured in hours, rather than weeks, challenged every assumption Japanese military training contained. Combat engineer Captain Hiroshi Yamamoto, captured during the subsequent American advance, provided insight into Japanese military thinking during post-war interrogation. We knew Americans had good equipment and many machines, but we thought they were still limited by the same natural laws that controlled our construction. When they built bridges underwater in complete darkness, we realized we were fighting enemies who had eliminated limitations we thought applied to everyone. The cascading failure of Japanese defensive strategy accelerated as reports arrived from other sectors describing similar American engineering achievements. The Philippines campaign revealed American forces building bridges across destroyed river crossings in timeframes that violated every calculation Japanese commanders had made about defensive timing. Mountain passes that should have provided weeks of defensive advantage became minor delays, measured in days, as American engineers carved roads through terrain Japanese forces considered impassable. The captured intelligence document translated as ATIS File 18756 revealed Japanese recognition that their entire approach to defensive warfare had become obsolete. American construction speed eliminates natural barriers as defensive assets. Rivers no longer provide predictable delays. Mountain terrain offers temporary obstacles only. Destroyed infrastructure is restored before defensive positions can be properly organized. Strategic planning based on engineering delays requires complete revision. This recognition came too late to affect Japanese strategy because their military system contained no mechanisms for adapting to construction capabilities they had never anticipated. Defensive positions throughout the Pacific had been cited based on assumptions about American engineering limitations that proved catastrophically wrong. Islands that should have been impregnable due to natural barriers fell to forces that built their way across any obstacle. The final psychological blow came from the realization that American construction operations continued despite direct military attacks. Japanese forces launching desperate assaults against bridge construction sites discovered that American engineers could fight as infantry when necessary, then return to construction work within minutes of combat cessation. This integration of construction and combat capabilities represented military evolution that Japanese traditional warfare couldn't comprehend or counter effectively. The October 24th dawn marked the moment when Japanese military leadership acknowledged that American engineering superiority had made their defensive strategy fundamentally unworkable. Natural obstacles that had determined military planning for centuries became temporary inconveniences that American forces overcame faster than Japanese commanders could adjust their thinking to new realities. The strategic consequences of American construction supremacy rippled across the Pacific theater with devastating effect on Japanese defensive capabilities. Within weeks of the Huon Peninsula bridge operations, similar construction achievements appeared throughout New Guinea, the Solomon Islands, and advancing operations toward the Philippines. Each successful overnight bridge construction reinforced Japanese awareness that their defensive strategy had become completely obsolete. The intelligence failure that enabled American engineering success proved impossible to correct because Japanese military doctrine lacked frameworks for understanding or countering construction capabilities they had never studied. Field commanders filed increasingly desperate reports describing American bridges appearing faster than their intelligence services could track or analyze construction operations. The systematic underestimation of enemy engineering capacity reflected institutional blindness that extended from tactical planning to strategic decision-making at imperial headquarters. General Douglas MacArthur recognized the strategic value of construction speed as a weapon that compressed the timeline of Pacific conquest beyond Japanese ability to respond effectively. His staff calculated that American engineering capabilities had accelerated the advance schedule by approximately 6 months compared to operations dependent on conventional military engineering methods. This time, compression eliminated Japanese opportunities to reinforce threatened positions, organize effective counterattacks, or establish secondary defensive lines. The psychological impact on Japanese forces extended far beyond immediate tactical consequences to fundamental demoralization that affected unit effectiveness across the theater. Combat reports filed by American intelligence officers noted declining Japanese resistance in situations where natural barriers had been rapidly overcome by American construction operations. Enemy units that should have fought desperately to defend strategic river crossings instead withdrew immediately when faced with American bridges that appeared overnight. The material consequences included the complete failure of Japanese defensive planning that had allocated resources based on engineering delays that American forces consistently eliminated. Fortifications positioned to control river crossings became worthless when bridges appeared at unexpected locations using construction methods Japanese engineers couldn't duplicate. Supply lines calculated to remain secure behind natural barriers came under immediate attack when American forces built their way across supposedly impassable obstacles. The technological gap widened as Pacific operations accelerated American engineering innovations that Japanese forces couldn't match or counter. Combat requirements drove development of specialized construction equipment, underwater foundation techniques, and rapid assembly methods that advanced military engineering beyond anything Japanese industrial capacity could produce. American forces gained access to technologies that represented generational advances over equipment available to enemy engineers. The logistical implications revealed American industrial superiority that overwhelmed Japanese resource limitations entirely. Bailey Bridge components, construction materials, and specialized equipment flowed through supply networks that maintained forward stockpiles despite intensive consumption rates. Japanese forces, operating with limited resources and extended supply lines, couldn't compete with material abundance that eliminated resource constraints as operational limitations. Admiral Chester Nimitz summarized the strategic impact in classified communications to the Joint Chiefs of Staff. Construction battalion capabilities enable operational tempo that enemy forces cannot match. Islands become bases faster than enemy can mount counterattacks. This compression of construction timelines compresses the war itself, providing strategic advantage that enemy cannot counter through conventional military responses. The operational consequences included the systematic elimination of geographic advantages that Japanese strategy required for successful defense. Mountain ranges, river systems, and island chains that should have provided months of defensive benefit became temporary obstacles that American engineering overcame in timeframes that prevented effective enemy response. Natural barriers that had determined military planning throughout history lost their strategic value entirely. The captured Japanese planning documents revealed growing recognition among enemy commanders that American construction capabilities had eliminated fundamental assumptions about defensive warfare. Staff studies acknowledged that engineering delays could no longer be calculated using traditional methods because American forces operated with technologies and techniques that existing military doctrine had never anticipated or prepared to counter. The casualty implications included thousands of Japanese lives lost in desperate attacks against American construction sites that continued operations despite direct combat. Enemy forces discovered that disrupting American bridge construction required sustained attacks that produced devastating casualties while achieving minimal operational impact. American engineers could repair battle damage faster than Japanese forces could inflict it, making construction sites nearly invulnerable to conventional military assault. The Strategic Bombing Survey conducted from 1945 to 1946 included extensive analysis of how American construction capabilities had affected Japanese military effectiveness throughout the Pacific War. Interviews with surviving Japanese commanders revealed consistent themes of technological surprise, strategic miscalculation, and recognition that American engineering superiority had made traditional defensive planning completely obsolete. Admiral Suemu Toyoda, final commander of the combined fleet, acknowledged in post-war interrogation the fundamental problem Japanese forces had faced. American engineers could build air bases faster than we could plan attacks against them. By the time our forces organized to assault their construction sites, aircraft were already operating from completed runways. This made defense of our perimeter positions impossible because enemy capabilities exceeded our strategic calculations. The institutional analysis revealed that Japanese military education had failed to prepare officers for warfare against enemies with superior construction capabilities. Staff college training emphasized conventional military factors like troop strength, artillery support, and tactical positioning while completely ignoring engineering capacity as a strategic weapon. This educational gap created commanders who couldn't understand or respond effectively to American construction warfare. The post-war economic implications included Japanese recognition that American industrial capacity had been successfully projected across the Pacific through construction capabilities that Japanese industry couldn't match or counter. The ability to transport complete construction systems to captured territories and establish immediate infrastructure development represented industrial military integration that Japanese planners had never anticipated or prepared for during their war preparations. The technological assessment confirmed that American construction innovations developed during Pacific operations had advanced military engineering by decades compared to peacetime development rates. Bailey Bridge systems, underwater foundation techniques, and rapid airfield construction methods became standard doctrine for post-war military forces worldwide. Japanese engineers studying these innovations acknowledged that their own military construction capabilities had been approximately 40 years behind American standards. The human cost included recognition that Japanese defensive strategy had wasted thousands of lives in attacks against American construction operations that were essentially invulnerable to conventional military assault. Enemy forces had launched desperate attacks against bridge construction sites, achieving devastating casualties while producing minimal operational impact on American engineering operations that continued despite direct combat. The intelligence failure analysis revealed systematic problems in Japanese information gathering that had prevented accurate assessment of American construction capabilities. Intelligence services focused on traditional military assets while completely ignoring engineering equipment, construction methods, and industrial support systems that determined American operational tempo. This selective intelligence gathering created strategic blindness that persisted throughout the war. The strategic reassessment included Japanese acknowledgement that American construction speed had eliminated natural barriers as defensive assets, making traditional military planning based on geographic obstacles completely worthless. Rivers, mountains, and destroyed infrastructure that should have provided predictable defensive advantages became minor delays that American forces overcame faster than Japanese commanders could adapt their tactics. The industrial comparison revealed that American construction equipment production had exceeded Japanese total industrial output in categories directly relevant to military engineering. Single American factories produced more bulldozers, power shovels, and construction machinery annually than Japanese industry manufactured during the entire war period. This industrial capacity gap made competition in construction-dependent operations impossible. The doctrinal evolution included recognition that American forces had successfully integrated civilian construction expertise with military operations in ways that traditional military systems couldn't match. The naval construction battalions represented organizational innovation that brought commercial construction efficiency to combat zones, creating capabilities that conventional military engineering units couldn't duplicate. The legacy assessment acknowledged that Pacific construction operations had established principles that continue to influence military engineering today. Speed of construction as a force multiplier, prefabricated components for rapid deployment, and integration of civilian expertise with military operations became standard doctrine for modern forces worldwide. The final strategic conclusion included Japanese recognition that they had prepared to fight American soldiers, but instead found themselves fighting American industry projected across the Pacific at construction speeds that made their defensive calculations obsolete. The war had been won as much by bulldozers and Bailey bridges as by battleships and bombers, representing victory of industrial civilization over military tradition that Japanese forces couldn't comprehend or counter through conventional means. The bridges that appeared overnight across Pacific rivers represented more than engineering achievements. They were manifestations of American industrial power that Japanese military tradition couldn't comprehend or counter effectively. Each Bailey Bridge spanning an supposedly impassable river, each airfield rising from jungle in impossible timeframes, each construction miracle that violated enemy expectations, demonstrated the victory of industrial civilization over military traditionalism. The Pacific War established engineering principles that continue to influence military operations today. Construction speed as a force multiplier, prefabricated components for rapid deployment, and integration of civilian expertise with military requirements became standard doctrine for modern forces worldwide. The Bailey Bridge system, proven in Pacific combat, became NATO's standard for tactical bridging and remains in use globally. Naval Construction Battalion organizational principles influence military engineering units internationally. Most significantly, the Pacific Campaign proved that engineering superiority could overcome geographic advantages that previous military doctrine considered decisive. Natural barriers that had determined strategic planning throughout history became temporary obstacles that superior construction capabilities could eliminate faster than enemy forces could adapt their defensive strategies. The deeper legacy was strategic. Pacific engineering operations demonstrated that technological and industrial superiority, properly applied, could compress the timelines of warfare itself. Japanese forces had calculated that natural barriers would provide months of defensive advantage. American engineers measured the same obstacles in days or hours, eliminating defensive planning based on engineering delays. The underwater construction techniques that stunned Japanese command represented the ultimate fusion of civilian industrial expertise with military necessity. Combat divers installing permanent bridge foundations, while enemy forces controlled opposite banks, embodied American determination to overcome any obstacle through superior technology and training. These operations challenged fundamental assumptions about what was possible in military construction under combat conditions. The psychological warfare aspect proved as important as the physical construction achievements. Japanese soldiers watching American engineers build bridges overnight were witnessing the future of warfare, where engineering capability determined strategic outcomes more than tactical skill or traditional military virtues. They had prepared to fight American soldiers, but instead found themselves fighting American industry projected across the Pacific. In the end, the Japanese command was stunned not just by the speed of American construction, but by the realization that their entire approach to warfare had become obsolete. The bridges built underwater in complete darkness were symbols of industrial power that traditional military thinking couldn't match. Sometimes, the fastest way to end a war is to build your way through it, eliminating every natural advantage that enemy strategy requires for success.